Morning. What are you doing?
Good.
Today we are continuing to prove the theorem of the optimal controller, and we will try to show where these formulas are coming from, because without that understanding of optimal control is more difficult. I can give you all of the formulas, but you will not understand, well, all of these formulas coming from somewhere, right? So you need to understand where they are coming from. Otherwise, there is no meaning just to learn by heart all of these formulas. Okay, so I summarized here everything we did previous time at the end of the lecture. Okay, so we proved the lemma, which is saying that Gramian of controllability is solving Lyapunov equation for any matrices, positive definite matrices P and Q. For any matrix, stable matrix A tilde. Right? And this is regular Lyapunov theorem practically. I found actual solution to any Lyapunov equation in a sense. It's a little bit complicated, but not too much. This is just some particular integral which solves Lyapunov equation, linear Lyapunov equation in that case. All right. Now, we wanted to prove that this is optimal controller. So this is the K optimal that we are looking for. Okay. And it will be given by R inverse, which is the weight of the input energy, times matrix B transpose times some matrix S, which is a solution of algebraic Riccati equation. Right. So you're solving that algebraic Riccati equation, this matrix equation. And this is also quadratic equation, which means it's not linear equation. But when you solve it, you get unique solution. And this unique solution S, you substitute it here, and you get optimal controller. Done. This is the optimal control, okay? But we want to show that this is correct, and this is minimizing Zj for given input, which is minus Kx regular feedback controller in state space, right? And last thing that we did, we gone to that state where we found the J, which is the same thing when we substituted x equals to the exponent times x0. If you remember, this is like solution of the equation and so on. When we substitute everything, we've got to that stage where you can write it as x0 transpose times that exponent times some matrix times some another exponent, and then again times x0. And since x0 is constant, you can take it out of the integral, right? Just constant vector. So I took it out here, and I took it out there. This is overlaid here, okay? And I define that integral which is left inside as S. So this is definition. Okay, I call that entire thing that part. I just call it S. All right. This is obviously some sort of matrix. I don't know what that matrix is, but I'm just saying this is my matrix. So by definition, this will be x0 transpose times S times x0. Right? But now look at that structure, okay? And compare to that structure. So given that structure, this matrix is practically my matrix A tilde. Because you have it here and there. Right? And this matrix is my Q tilde. Same structure. So this is same like P. Okay. When I substitute Q tilde equals to that thing, and A tilde equals to that thing. Same thing. So we know that that S, which is same as P, solves that equation. So I just need to substitute to that equation appropriate A tilde and Q tilde. And this thing will solve that equation. So let's see what we get when we substitute into the Lyapunov equation and see what happens. Because we know that this is correct for that matrix S. Right? It's just particular case of A tilde and Q tilde. So let's see what do we get here. I'm substituting into Lyapunov equation. Let me just move the camera. So what do we get here? So Lyapunov equation will look like that. You'll have A minus BK transpose times S, that long integral, whatever it is, but it is some sort of matrix, right? Plus S times A minus BK, just write in the Lyapunov equation, equals minus Q tilde. But minus Q tilde is minus Q minus K transpose K, right? So like that. So this is what you get from that. This is Lyapunov equation, so we know that this should be correct for that particular matrix S, okay, which we defined as an integral. Any questions so far? So, and we know that this matrix is always stable because it's closed loop matrix, right? So we know that in closed loop system needs to be stable. All right, so let's do some manipulations on that. Let's open the parentheses here. That will be A transpose S minus K transpose B transpose S. So this is the first part, plus SA minus SB K plus Q plus K transpose R K equals matrix of zeros. Just algebra. I open parentheses, move that thing to the left side with minus sign. Right? So far. Okay, and now the most difficult part, tricky part. I will add and subtract particular matrices to combine different terms here together. Right? This is overlay. It will look like magic because I'm just introducing some weird matrix and I'm saying let's add that matrix and then we will subtract that matrix. Obviously, I'm not changing anything. But you'll say, like, how would you even guess that type of matrix? How would you know that you need to add that particular matrix or some other matrix? Okay. So it's technically simple, but you probably haven't learned that in linear algebra. But maybe you learned that in regular algebra. Do you remember what completion to squares is? Completing to square some thing. So you have, let's say, quadratic polynomial of some kind, you have all kinds of things, but you want to factor it somehow. So you're completing it to square. So you're saying it will be something plus something squared, and then the leftover will be whatever is left from that square. Okay, so completing something to a particular square. Okay, so you want to write like s squared plus as plus b as s plus something squared plus something whatever number. Right? Same thing here in linear algebra. It just looks more complicated. Okay, it's just more complex to write, but same idea. You're practically adding and subtracting the same constant number, which would offset whatever you put it in the square part. Right? This is how it technically works. But I'm showing that as like, this is what you will need to get. Right? So I'm copying the same thing first, moving that thing here. And then we don't have to move here. Maybe we'll add the matrix. So it will be minus K transpose. Then I will multiply and divide by R. And you know that R is invertible because it's positive definite, right? So you can have something like that. In a minute, you will understand why I need that B transpose S. So I'm writing that part with adding that part. Obviously, I haven't changed anything. I just multiplied and divided by the same matrix. Again, division by matrices is prohibited. I just multiplied by inverse of the same matrix, which makes that matrix I. So I haven't changed anything. So it's legal thing to do in linear algebra, okay? So I replace that thing with that thing. Plus SA. Same thing I'm doing with that matrix. It will be plus minus S, B, R. But in that case, it's in opposite order. K. Right? Plus Q plus K transpose R K. And now that part which is completion to squares, which will be S, B, R inverse B transpose S plus and minus the same thing. So I practically added that matrix and then immediately subtracted that matrix. And this is kind of like, where is that thing coming from? So this thing is coming from that thing completion to squares. Okay. You're trying to write quadratic equation here, like with matrices. All right. But it's clear that this is equivalent to this one completely, and haven't changed things. I just multiplied by matrix R, inverse of R, so haven't changed anything. Added some matrix, subtracted the same matrix. Haven't changed anything. But now the thing will be written as the following thing. So it will be A transpose S plus SA plus Q, which is coming from here. I'm using this one, and this one first. Okay, so I have them written together. And then I get the following nice quadratic thing. S, B, R inverse minus A transpose times R times the same thing without transpose. What I wanted to get. Practically, if you open in this parenthesis, you will get that expression. Okay, you just multiply S, B, R inverse R by R inverse B transpose S. You'll get one of this. Then you get S, B, R inverse times R times minus K. So you'll get R inverse and R cancel out, so you'll get S, B, K is minus, right? Which is S, B, K is minus, right? And then you'll have minus K transpose R, K, minus and minus cancel, so you get plus K transpose R, K, which is this one, right? And then you get this one, and this one will be minus K transpose R, cancel out, so it's minus K transpose B transpose S, which is also one of this. Okay, this one. Same thing. But now we have very nice description of what we actually need here, okay? Because, and I'm missing something. Obviously, need to add one of these terms. So you will get that term. Minus S B R inverse B transpose S. Okay. So this is equivalent to this one. Now, what do you see here? Now we need to solve that equation somehow, right? So what would be solution to that equation? And you have two unknowns here. You have S, which you need, and K. These are two things that you can play with. So you need to choose S and K such that they will solve that equation. So what will you choose? So if you're looking at that part and that part together, you want it to be 0. And that part you want to be 0. This part together is this part. And this is exactly the solution that we are looking for. Because if this part equals to 0, right? What do you get there? It's exactly that thing. Okay. Now, for the second part, which is this one minus this one, this is Riccati equation, right? This is that thing. This is exactly that thing. So if two of them together equal to 0, then that entire thing equal to 0, right? So the overall idea is that you choosing such K and such S, which satisfy that thing. And practically this is showing you that you get correct solution, an optimal solution. But we haven't discussed what is optimal here really, which is interesting question. Yes.
If this thing is equal to 0, we have the same thing as the K optimum, but with a minus. With the sign.
What's K will be minus SBR inverse. This will be minus that thing. Yes. Right. So that's the equation. The original equation was different. Let me see just a second. The previous one was correct. My formula was a case in point. Okay, so this is minus, minus, this is plus. Okay, this is the formula. So K is positive, minus is coming here, right? Minus is coming from the actual negative feedback. Okay, thank you for catching the mistake.
You said like the last one and the first 3 terms is equivalent to that equation. But isn't the
So the first 2 terms, first 3 terms there, and the last term are equivalent to that entire thing.
but
It is
the order
supposed to
of
be.
the B transpose, does that matter? Like
What
that
transpose?
That one's S, B, R -1, R like to the inverse, and then B.
In this part?
No, for the last term.
This one?
Yeah. And like the equation over here, it's S B transpose, R inverse B S, but then that one's later.
B transpose comes first. Let's see. Transpose comes first. So it's this one's supposed to be there. Let's see. So this one's supposed to be the transpose. First. Well, I will check that and we'll come back to you. Yeah, you're right. This is supposed to be transposed here potentially. Let me see in the original definition how it goes. Just copy it and correctly probably. Yes, it should be. Be transpose, right? So this is incorrect. This is supposed to be transpose. You see, proof's helping us to figure out some mistakes because the proof looks correct. I just copied this one incorrectly. All right, so this is a controller, and this is the Riccati equation that you need. And in lectures, it was correct. Just copied it today incorrectly. All right. So this is the right equation. Now, any questions on the actual proof? Too simple? So here are a few critical questions about the proof, which I want you to think about. First of all, typically when you are proving anything which is optimal, you're minimizing something, you're maximizing something, you're doing some derivative equal to zero of some kind, right? Or you are using some other things which are saying that this is actually optimal solution or minimal value that you could get. But here we just said, well, let's go with the algebra. And if the value is like zero, then everything is good. Like if you solve that equation, if you found that solution, and this is clearly a solution of that thing, right? Is it the only solution of that thing? Probably not. But I'm saying if you found that solution which solves that, which means you choose K which solves that part and S which solves the rest, and you get zero, then it's good enough and it is optimal. So think, and I practically almost never used any of that thing, right? I haven't used that this is stabilizable. I haven't really directly used any of these assumptions on the positivity and other things. I just said generic matrices. I used only assumptions that R is invertible, practically speaking. Said, well, if R is invertible, I can use that kind of thing, right? I can invert it. But I haven't really used that this is positive definite in anything. Not really, not directly, right? I haven't used that this matrix is positive definite. This matrix that we are using that matrix, right? Like Q plus K transpose RK, I haven't even shown that this is positive definite. So why would I use it even in Lyapunov equation? Right? I never showed anything like that. So the question to you is why? Why it still makes sense to use anything like that? And this is a difficult question, actually. So think about that question. If you can come up next time with some solutions, you can get bonus on that. Like why I don't really need to get into that, into all these assumptions and do all of the other things, like proving that this is positive definite or, all these things. I just showed like I have that one solution, and this one solution is magic optimal. Why is that? All right. Okay. Any other questions on that? So now we will solve a few problems in that domain to see how the actual optimal computation. Can I delete that part? Okay. How the optimal controllers work. how we compute them. We will do exercise by hand, but obviously nobody is doing that by hand. You can do that with computers. And all these computations will be done by a single line of code. Okay, so here is the question. You have camera. X dot equals x plus bu. Y equals cx. That's my system. Matrix A will be -2, 0, 1, 0. Matrix B will be 1, 1. Matrix C will be 0, 1. Right. So that's my system. I want to design optimal controller. And my J will be what I want to optimize. It's integral from 0 to infinity. Y squared plus u squared. Something simple. Okay. So in that case, rho equals to 1. This is what 6 multiplies this thing. And Q is C transpose C. You remember how to get y squared instead of x transpose Q x. Okay. So solution. How you find the optimal controller? Let's try to solve Riccati equation first to find the matrix S. So here's my Riccati equation. A transpose S plus SA plus C transpose C, which is of matrix Q, minus S B transpose S equals to 0. And since rho equals to 1, rho inverse is also 1, right? So this is fitting here. Typically you have like SB times R inverse times B transpose times S, right? That's what you have there. Question so far? Why we have that equation? Okay, so let's substitute all of the matrices and see what happens. So we will substitute that S equals to S1, S2, S2, S3. Since this is symmetrical matrix, it needs to have same element here and there. Then we'll have 3 quadratic equations instead of 4. And pay attention that this S numbers has nothing to do with eigenvalues or anything like that. This is just incidental that they also call S, because they are elements of matrices. Nothing to do with the roots. Okay, so let's substitute that. So A transpose will be -2, 0. Here's 1, 0 times S1, S2, S2, S3 plus SA, which is again S1, S2, S2, S3 times matrix A, which is -2, 0, 1, 0 plus C transpose C will be 0, 0, 0, 1. Okay, like that's that type of vector times that type of vector. That's 0 by 0, 0 by 1, 1 by 0, and 1 by 1. Right, these are the elements of that matrix. So this is C transpose C. And then you have that difficult and long matrix S1, S2, S2, S3 times B transpose, and B would be, practically speaking, 1, 1 times 1, 1 That will be 1 times 1, 1 times 1, and so on. So all of them will be obviously ones. 1, 1, 1, and 1. All right. And times S1, S2, S2, S3 equals to 0, 0, 0, 0. Matrix of zeros. Now we need to write all these equations. Okay, so we have 4 different equations. For each element, you'll have 1 equation, quadratic equation. But this equation and this equation should be kind of symmetrical in a way, so 2 equations should be the same equation. So technically, you'll get 3 equations with 3 unknowns, S1, 2, and 3. All right? So let's write it more explicitly. So first matrix will be minus 4S1 plus 2S2. Here you have element minus 2S2 plus S3. And here you get minus twice S2 plus S3 and 0. This is the first matrix from that part. Plus matrix 0, 0, 0, 1, which is that matrix, and minus the quadratic matrix, which will be S1 plus S2 squared, S1 plus S2 times S1 plus S3, and then same thing here. And S2 plus S3 squared equals to matrix of zeros. Right? And we get system 3 equations. Do you understand how I got from this part to this part? So it looks like minus 2 times S1 plus 1 times S2 plus S1 times minus 2 plus S2 times 1. Combine them together, you get something like that. And so on for each one of the rows and columns. Okay, now we have that equation, which is Z thing plus Z thing minus Z thing equals 0. And then Z thing plus Z thing equals 0, and so on. You have practically 4 equations, but 2 of them will be the same. You're left with only 3 equations. So it will be S2 plus S3 squared equals 1. Second equation will be S2, S1 plus S2 times S2 plus S3 equals minus twice S2 plus S3. And third equation, S1 plus S2 squared equals twice S2 minus 4 S1. That kind of equations. Now pay attention that all of them are quadratic equation. How many solutions you might have for that system? Total. You have 3 variables and 3 quadratic equations. How many solutions you might have? You might have up to 6 different equations, solutions to that equation. Okay. So in that case, you might have 6 different solutions, and you need only one, unique one. Okay. The one which will give you S, which is positive definite. How do you know that some matrix is positive definite? Like easy test for symmetrical matrices. Do you know how to identify very easily that matrix is positive definite? It's called Sylvester criterion. Especially for smaller order matrices, it's very convenient criterion for symmetrical matrices. And it says if the matrix is symmetrical and positive definite, all of its minors on the main diagonal will be positive, which is interesting. Remember what minor is of the matrix? So like if you have particular matrix, whatever size, you're taking that corner, making determinant, that corner, making determinant, that corner, making determinant, and so on. Okay, so all of these determinants need to be positive, which means that corner number, determinant of a number is number, right? So this number should be positive. This number times this number minus this number times this number should be positive. And determinant of 3 by 3 matrix need to be positive, and so on. Okay, so taking all these corners, computing all of the determinants, all of them need to be positive for the matrix to be positive. This is a Sylvester criterion, right? Relatively easy for smaller matrices. In our case, to identify that some matrix S, which is S1, S2, S2, S3 is positive, means that S1 is positive and S1, S3 minus S2 squared positive. These are the conditions, right? So this is determinant of the entire matrix, taking that corner and taking that corner on the main diagonal, which means S1 is positive and S1 times S3 minus S2 times S2 is positive. If that's true, if these conditions are true, then this matrix is positive definitely. So you need to choose S1, S2, and S3 such that they will do that. This is the overall idea. Okay. Now you need to solve and to find, practically speaking, 6 solutions for that, for trying to guess what the solutions are in a way such that this will be true. So this is where the difficulty is, right? Because, well, even solving 3 quadratic equations is already a problem. How would we solve that? So we need some transformation variables here, maybe, or some other substitutions. So pay attention that multiple different things are repeating here. Okay, so you have, for example, S1 plus S2 as a single element here. Okay, you have S2 plus S3 as a single element here in the multiplication. So you might be able kind of to use that property somehow. Because, for example, if S2 plus S3 squared equals to 1, and you have S2 plus S3, so this thing might be +1 or -1. That's it. These are the options, right? Because this is square root of 1. The square root of 1 might be +1 or -1. Because -1 squared or 1 squared will be equal to 1. So the solution of that one is practically S2 plus S3 equals ±1. These are 2 solutions. Okay, so far, this is school algebra, not linear algebra. This is basic algebra. How you solve system of equations, all right? So let's see how we can represent that thing. This is, if you algebraic trees. You can write that thing as S2 plus S3 minus 3S2. Almost like completion to squares of linear version of it. All right. So you have to write that thing as S2 plus S3, and then you get that one left over here, right? So you need to put it here somewhere. But this will be kind of our new variable, S2 plus S3, because it's easier to work with S2 plus S3. Same thing we are doing with S1 plus S2. So we want to get rid of that kind of thing and to write it as a function of S1 plus S2 plus something or minus something, whatever that something is. Okay. So let's see how it looks like. So this thing will be -4 S1 plus S2 plus 6S2. So pay attention that now it's much more convenient to work with variable S2 plus S3, variable S1 plus S2, because you have them everywhere, and variable S2. So now you have 3 new variables. You don't have to transform it, but it's just more convenient to solve it that way. You just need to work in order to solve it. So let's choose. Okay. So you can choose this one, +1 or -1. You can choose this one also as positive or negative because we're doing square root, right? Square root is always plus minus solution. Okay. So let's start the actual solution. So we have, let's choose S2 plus S3 equals to 1. Obviously, if this doesn't work, you need to switch and choose it -1. Okay, this is where the difficulty in hand computation is. You need 6 solutions, but you are trying to guess one which is working somehow. And since you're expecting this one to be positive, okay, probably all the numbers should be somehow close to positive, at least for that case. So hoping that this is +1 and not -1, though nobody promises you anything like that. So given that, you have, so when you substitute that thing to the second equation, what you get is S1 plus S2 times S2 plus S3 equals S1 plus S2, because this is 1, right? And equals your previous equation, which was S2 plus S3 minus 3S2, which is that thing here. But this one is 1. That's 1 minus 3S2. And plus S2. Right, so it's 1, wait a second. S2 plus S3. So S1, yes. So from here, S1 equals 1 minus 4 S2. Okay. I'm just moving the S2 here. So we've got something linear here, we've got something linear here. Okay, and from the third one, you get S1 plus S2 squared equals -4 times S1 plus S2 and plus 6 S2. So 1 minus 3 S2 squared equals -4, 1 minus 3 S2 plus 6 S2. I'm just substituting all of the variables to make it all a function of S2. Right? Substituting that thing here. Okay, now we have that quadratic equation after few lines of opening parentheses and so on. Everything is a function of S2 now, but it's quadratic. So it will be 9S2 squared minus 24 S2 plus 5 equals to 0. You get quadratic equation in S2, and you have two rules. S2 equals will be 24 plus minus square root of 24 squared minus 4 times 9 times 5 divided by 18. And you will have 1/3 times 4 plus minus square root of 11. Something like that. So you found two variants of S2. Now, for each one of these variants, you obviously can find all of the other solutions, okay? Which means it will be many different solutions available here, okay? So let's try to substitute it further, okay? From here, you'll get S1, so this is S2, right? Two of them. It will be 1 minus 4 S2, right? This is coming from here. And then you get also, obviously, multiple solutions. 1 minus 4/3, 4 plus minus square root of 11. And S3 is 1 minus S2, which is coming from here. No, not from here. So S3 and S, where is that connection? S3 and S2. So this is that part. B plus 2.
It's from your.
Oh, it's from the first equation. This is that part. Okay. So this is coming from here. That's correct. Right? And this will be 1 minus S2, which is that thing. To have multiple different solutions for a given choice. Now you have to choose a matrix. And you have multiple variants. So you need to check all of them. But typically you start always with picking all of the positive numbers. Okay, bigger numbers everywhere you choose plus. Okay, there's all of the possible combinations. And eventually you will get matrix like that. This matrix will be positive definite. Now pay attention that I think S1 should be positive, right? So it needs to be positive based on that thing. So you might be able to filter out one of the solutions if one of them is negative. Okay, probably one of them will be negative. Like if this is plus here, then this number will be pretty big, and 1 minus big number will be something negative, right? So you need to choose minus here, most likely. Okay, so you have a few ways to filter out and not to check all of the possible solutions. Okay, but it's still a lot of headache to figure out one of the possible solutions, especially for higher order systems. It's second order, which is relatively simple, right? Or almost trivial system, but you still have multiple solutions to check. All right. So this is positive definite. And your K matrix will be 1 divided by 1, which is 1 divided by rho, B transpose S. This will be 0.3136 and 1. This is your optimal controller. It's a lot of algebra, right? A lot of it. Any questions on that question, on that problem? Okay, we'll give you a little bit of time to copy that. So you need to remember that these particular numbers do not matter, and I'm giving them technically because I want to solve the same problem next week in a different way. So I'll talk about symmetrical root locus, which is different technique of finding directly locations of optimal pole locations. Instead of going through Riccati equations and all that stuff, we will find directly location of optimal poles without going through Riccati equations and that kind of stuff. So I'm planning to get to the same answer with new technique, okay? So just kind of remember these numbers in a way that you'll get to the same numbers next time in a different way, right? Any questions? Okay, so another exercise, a little bit more complex in terms of J function, all right? So have same type of system, matrices ABC, 0, 1, matrix C is 1, 0, and J like that. So J will be some expression 2x1 squared plus twice square root of 2 x1 x2 plus twice x2 squared plus u squared, something more complicated. And we want to find K and J minimum. J minimum for initial conditions which are 1 and 1, initial state. Obviously, J is dependent on initial state, so we get different numbers. Okay, so what should we do? How do you solve that? First of all, we need to identify R and Q. So this is what we need to do to solve the Riccati equation. So what is R here? R is something which multiplies Q squared. What multiplies U squared? 1. 1. R equals to 1. Call it R or rho, same thing. For C systems. What is Q? This is 2 by 2 matrix, so you need 4 numbers. That is symmetrical, so technically 3 numbers. So what are those 3 numbers? It's quadratic form, remember? What are the coefficients of quadratic form? What they multiply? So main diagonal multiplies squares of the space, which means whatever multiplies x1 squared is here, it's 2. What multiplies x2 squared? 2. And now you have something which multiplies x1 times x2, and another thing which multiplies x2 times x1. So what would that be? And it is symmetrical. So this is that part, right? We need to write something times x1, x2, plus that same something times x2, x1. So what is that something? Square root of 2. That is exactly what you have here. So it needs to be the same thing. So taking just that thing, dividing by 2. This is your Q matrix. And if you will try X transpose QX, you will get exactly that thing. All right, this is quadratic form. All right, so now let's solve the Riccati equation. Okay, so it will be same thing as before. 0, 0, 1, 2, just A transpose times S1, S2, S2, S3. So I'm going fast through all these computations because we've done that before. S1, S2, S2, S3 times A matrix 0, 1, 0, 2 plus matrix Q minus S1, S2, S2, S3 times 0, 0, 0, 1 times S1, S2, S2, S3. So R is 1, so we can ignore it, equals all the zeros. So what you will get, it's like 2 here, S1 plus twice S2 plus square root of 2. Here you'll get S1 plus twice S2 plus square root of 2, twice S2 plus twice S3 plus 2, minus S2 squared, S2, S3, and S3 squared equals to matrix of zeros. To get again 3 quadratic equations, 3 unknowns, and you have multiple different solutions. You're picking the solution which is positive definite for the matrix S. So you will get something like S2 squared equals to 2. You'll need to pick the right value here. One out of this. So if you choose negative value, it will not be positive definite. So you're picking positive here. Again, I'm not going through the process because this is kind of trial and error process, or you can solve them all and then pick the one which works. And you'll have only one which works. Okay, out of all possibilities, you have only one which works. One unique solution. This is promised by the theorem that we discussed before. So the correct S will look like that. 1.104 minus square root of 2, 0.219. Okay. Oh, sorry, this is not the right one. This is what you get with the minus sign. So you choose a positive one, you get 2.7878 square root of 2, 4.9713. This is positive definite. How do you know that this is positive definite? This one is positive. This one times this one is more than this one times this one, which is 2. The 2.7 times 4.9 is more than 4. Obviously. It is positive definite. Okay, controller will be same formula. B transpose S. That will be square root of 2, 4.9713. J optimal or minimal will be x0 times S times x0. And when you compute that, you get 10.5875. Okay, so this is the solution of that question. Our camera is practically dead. It's interesting. Responsive. Nice. Nice blue screen. All right. So the question becomes, where are the optimal pole locations now? What do you think? So we found the optimal controller, whatever it is, the optimal. It is minimizing that complicated G. But where are the poles? Because we said, like, well, previously we could put poles anywhere we want for controllable systems. We said, well, we will decide where the poles are based on their properties or whatever. And then we said, well, we actually don't know where to put them, so let's design some optimal controller based on minimization of the function. And this will give us the location of the poles, and we will design it wherever we want them to be. Okay. But my question is, like, where are they? I haven't used it anywhere here. How would you know? Now your question is, where are the poles? How do you know where the poles are? So you design the controller, you put it in closed loop, right? You have some closed loop poles. Where are they? How do you know? How can you compute them? The function you can, should you? But do you want to compute? You can, yeah. Closed loop transfer function. Then you find the location of closed loop poles, yes. But do you need to go that far? You need only the bottom part of the transfer function, right? That's all you care about. You need to compute characteristic polynomial. So what is the characteristic polynomial of that thing in closed loop? What is closed loop matrix that we are talking about? This is the matrix in closed loop. You're finding eigenvalues of that matrix. These are your closed loop poles, optimal ones. Okay? So this is easy way to get them, right? You're just finding eigenvalues of that matrix, A minus BK matrix. It's closed loop matrix, right? But next time we will talk about a completely different method to get to the poles first. So you'll find the poles of that matrix without computing K optimal. And we will compute K optimal given the poles, using all of the techniques that we learned before. So before, if I'm giving you location of poles, you can compute the controller, right? 3 different methods like Basgura, Ackermann, comparison of coefficients, all of that stuff, right? So if you know where to put the poles, you have multiple methods to do that. But in that case, you can compute it just from location of poles. So next time we will go that direction. So we'll say, oh, the optimal poles need to satisfy particular properties. So they have particular properties, and you can compute that from transfer functions actually without going through Riccati and other complex stuff. Okay. So computationally, it will be much easier. In a sense, it will work only for CISO systems. You have extension for MIMO systems as well, but we will not talk about that. For relatively simplistic J functions, you can do that and start with poles first, and then find controller, which is always the same controller. And this is why I wanted that exercise to be relatively easy with particularly simple J function, okay? Because for that function, you can find it in a different way. For that type of function, you can find that in a different way as well, but it's just more complex and more complicated, more sophisticated computations and so on, okay? So this is the idea that we will be working on next time. And do you have any questions? All right, thank you. That's it for today.